Yeah, so it's kind of a casual Friday, so I'm wearing my birthday shirt that I got on Wednesday nights. It says, uh, chemistry is a lot like cooking, just don't lick the spoon. Okay, and so we all know that. Don't lick the spoon. This one, I wanted to talk about this one though. Sometimes people get confused with point groups with the different kinds of structures. And so I just want to emphasize this because I don't know that anybody has in your education. That is, there's a lot of different things that we call structure. Okay, we have lots of different ways to write structures, and of course one of those is the Lewis dot structure. So that's a very particular type of structure. But this one is the one that I think sometimes people get confused about, and that's the electronic structure. So that's the structure around individual atoms or maybe for the whole molecule. And so when making water, if we look at that oxygen, we see that it has 4 electron domains. And if we're doing the local bond theory, we count those up. 1, 2, 3, 4. And we say if it has 4 electron domains, it's sp3 hybridized. We have to have an atomic orbital for each one of those to form a local bond hybrid. And that is in a tetrahedral arrangement around that atom. It's not, listen carefully, it's not saying that that molecule is tetrahedral. So it broke my brain one time. I was like the manager here. It's like someone told me water on a test was tetrahedral, and I was like, how could you even say that? You know, tetrahedral is methane. You know, it's 4 things around a central atom. But then I realized they're getting this mixed up: electronic structure and molecular structure. So molecular structure is the shape of the whole molecule, not just any individual atom. So that's the thing we run through the flow chart. So we need to know the electronic structure around each atom so we can make the molecular structure accurate. But then we take the whole molecule's structure through the flow chart and come up with the point group. And so water would be called bent. It's a bent molecular structure because we just use the atoms to name the molecular structure. Notice we're ignoring those lone pairs. They're there to give it that bent shape, but when naming the shape of the molecule, we just use the atoms in their positions. So it's a bent molecular structure, and then that ends up being a point group of C2V. So I'm not going to throw you out of the window if you say that. If you say tetrahedral, I might. So today we're going to use symmetry. So we're going to do what SpongeBob does. We're going to throw away calculus, and we're going to use symmetry. What's that? Yes. Although you have one more lab, I think this is the Calculus Week lab where you're going through all the calculus, and now you'll really appreciate symmetry. It's just do it, right? So that you feel how bad it is. So, so that when you get to symmetry, you're like, now I get why science loves symmetry, you know. So that's, it's an exercise in contrasts, I'll say it that way. Okay. And so where are we? Well, we've done Lewis dot structures and come up with Vesper shapes and geometries. Then we got the point groups. Now we identified the character tables. We looked at those last time and assigned the Millikan symmetries, this piece right here. Assigned the Millikan symmetries of the molecular motions, remember the dance moves, the molecular orbitals, the oscillation of the cloud. Okay, we didn't do anything with NMR, but you could if you wanted to. And then now we're going to look at a different set of tables called the direct product tables. So these direct product tables are all of the multiplications of all the rows possible in a character table. And those are what allow us to determine the selection rules for spectroscopy. So each of these wave functions will be a different irreducible representation or row in the character table. That's R, R-O-W, row in character table, CT. Okay, and so this direct product, this sort of, you know, multiplication sign inside the circle is just how you would multiply vectors, right? So you would just multiply, you know, number A, you know, the first number times the first number and the second number times the second, but you don't sum them together. It's not a sum product. It's just direct product. And so this is specific to the point group. So we've got to have the point group correct and with character table correct before we can do the direct product table. So we know this is related to the integrals, the intensity of a transition. And so this is that wave function x which represents light, times the initial wave function, and then we multiply the final wave function, and we integrate over all space. And if that's non-zero, then we would say that that transition is allowed. So if the results of this direct product table, so these three things together, does not contain, and we have to say that word particular, it doesn't say it must contain the totally symmetric irreducible representation. If it does not contain the totally symmetric or top row of the character table, then the intensity is zero, and we would say it's forbidden by symmetry. So let me emphasize this so importantly. If the result of the direct product table does not contain the totally symmetric irreducible representation, in other words, that top row of the character table, then the transition is forbidden by symmetry. But even though the photon of light matches the difference between those energy levels, if the wave function symmetries don't allow that transition, then the light will go right through. Okay, it might slow down, it might interact like just instantaneously, like the electrons oscillate or whatever, but it's not going to absorb that photon. So it'll go right through.
A1 person can be A1.
Yes. Mm-hmm. So sometimes for things with threefold symmetry where we have E, and that was on the test, like E times E, where we got three things, but one of them was A1. So when I say contain, it means in that situation, we have three functions plus each other, but one of those functions has A1 symmetry. So that's good. So this is what we do. We use the Vesper theory to get the geometry, find the point group, find the symmetry of the wave functions, and then select the symmetry of the spectroscopic interaction. So we have two different types of spectroscopic interaction that we're talking about, two categories. The first category is absorption and emission. It sounds like two things, but they have the same interaction. It's a single photon. So a single photon is absorbed, or a single photon is emitted. And so we just use X, Y, or Z to represent the polarization of that light. So the oscillating dipole moment can be plane polarized along the Z-axis, or along the Y-axis, or along the X-axis if it's going that way, or vice versa if I got those screwed up. Okay. Now the second spectroscopic phenomenon we're dealing with is scattering. And there's two different types of scattering. There's Rayleigh scattering and Raman scattering. And we would use those X squared type interactions because it's two photons. So I don't know if it's exactly like classically correct in terms of physics, but the way I think of it is the photon comes in and the photon goes out. So like if it comes in on the Z-axis and it goes out on the Z-axis, then because it's scattered, right, that photon comes in and bounces off. If it comes in on the Z-axis and leaves on the Z-axis, I would consider that Z squared. But what if it comes in on the Z-axis and then leaves on the X-axis? Then that would be the XZ interaction. So it could come in, plane polarized on the Z-axis, interact with the molecule, and maybe the interaction is some sort of rotatory motion, and now the photon comes out. It's been rotated. It was Z, now it's Y, or now it's X, and it comes out. And so those would be the two photon combinations of XY, XZ, or YZ. So we have, those are the options of what goes in the middle of our integral. And then we would use the direct product table for the point group to determine the symmetry of that transition dipole moment integral to see if it's zero or non-zero. So let's go back and do the particle in a box just to review. We only have E and I symmetry elements. So we don't really have a molecule, so we couldn't really do the flow chart on this one. We just had to say, what can I possibly do to this wave function? And all I can really do is invert it, because it's just one axis. You can't rotate it to another axis. You can't do anything else. So we can just invert it. So we just have the CI point group and the CI character table. Really just done by what they call, just done by inspection. Okay, we only have the x-axis. And so then there's our character table up there. And so then we have labeled our wave functions. N equals 1 is even, N equals 2 is odd. We can go back to that lecture if you want to look at that, but just look how it's around 0. You see they're the same on both sides or the opposite sign on both sides, and that's a quick way to do it. That's why I center my wave functions on 0. And so we set up our dipole moment integral for absorption or emission, where we have one photon of light coming in, interacting with the lower state and the upper state. So we're asking, is this transition allowed? So we can put in those numbers, 1 and 2. So we have wave function 1, wave function 2, and x. And what we want to do is we want to insert the symmetries of those. So we have wave function 1, which is AG, x is AU, and wave function 2 is AU. Okay, this is where we need the direct product table. We have the character table. Notice what's in the character table. You have down the first column the A, U, and AG, and then we have the characters in the middle. Look at the direct product table. It doesn't have any characters. It's just direct products of those rows. So we have all the possible combinations of AU and AG times each other. Now this is a very simple character table. It only has 2 options, AG and AU, so it's just a 2 by 2. If we have like D6H where it's got, 12 or so rows, it's going to be a 12 by 12. So some of the direct product tables are pretty big. And so then we use this table to simplify these multiplications. And so we have AU times AG. So we have this one here, AU times AG gives us AU. And you see that's where we got this guy right there. Then we do it again. AU times AU. So we have this one here, comes across, and it's AG when we multiply those together. So we got this guy right here. And now we're done. We don't have any more multiplications to do. We have the integral, that's what Dirac notation says, integral over all space of a function that has top row symmetry. So that's non-zero. Okay. Therefore, the 1 to 2 transition is allowed. So this is, again, just a review. We've done this before, but it's just good to put it here because we're going to do some more complicated ones. Okay, so let's flashback. Can we do this in general? We know that this is going to always be the same here. If we say started in this AG and went to that AU, then that would be the same. If we started here AU to AG, we would swap these two. Okay, but then it would be AU times AU, which is AG, and then AG times AG, which is AG. So going from U to G is fine. Going from G to U is fine. What about going from G all the way up to AU? Yes, that's fine as well. So we have the selection rules for, yes?
The AG
Where's this, AG squared?
right there, at the bottom of the interval.
At this bottom one? This line here? Yes, so this is the top row symmetry. So we're doing an integral over all space of something that's even. So the only row in a character table that's even is the top row. So that's why I'm beating that. And so all integrals of odd functions, let's just take this green function. If we integrate just this function from left to right, so we start over here, we start summing that function, we get a lot of positive values. So at this point it's positive, but then we start subtracting and they're even. They're the same magnitude. So I'm going across, I'm getting more and more positive, and then I hit this point and I keep integrating. So it means I keep adding that function in and I get all these negative numbers and it goes to 0 when I get to the end of the box. So the integral over all space of an odd function is 0. This one obviously is non-zero. If I start here and I add it all up, I get all positive numbers and I get to the end and I've got a non-zero result. Same with this one. I get positive numbers, but then I get some negative numbers, and that here is canceled out, but then I get some more positive numbers and it's non-zero. And it's smaller, but it's non-zero. So that's just integrating a single function. If I take functions times each other, it gets crazy complicated by hand, which is what y'all are doing, but it's still easy using the direct product table. So we're just looking at the symmetries to simplify all of these things. So this is the symmetry of wave function 1 times x, and that's the result. And then we have that result times the wave function 2 and its result. And so we're just looking at the symmetries, and if we get top row here, then it's non-zero and it's allowed. So it's just really super easy, all on one single post-it note. So all of those AG to AUs are allowed, and also all AUs to AGs are allowed with the single photon of light. Okay, so these are our selection rules, plus or minus 1, 3, 5. Those are all the situations where you have a G to U or U to G transition using a single photon of light. Let's do Raman. Okay, so scattering, Raman and Rayleigh actually. So this uses the x squared operator. So this is what's going on. We have this light coming in that doesn't match any of the energy levels. So incoming light, scattered light. Can light cause this transition to occur with scattering? So it comes in with green energy and it leaves with red shifted, so a yellow photon comes out if it were to get to this level. Is that allowed? So can it go to 1 to 2? So we'll put 1 and 2, and we have x squared in the middle. And now our symmetries. Where do we get the symmetry of x squared? Well, we go over here to the character table and we find x squared. It's pretty easy, right? So that's why we have those extra columns in the character table. They've already figured out the symmetries of all these different things. And so then this AG goes right here in the middle. That's where that came from. And then we do the direct product table. So AG times AG is AG. And then we have the n equals 2 wave function is AU. And so that kind of wrecks things. AU times AG is AU. And so now we have the integral over all space of something that's not the top row. So it's equal to 0. And that's what SpongeBob was complaining about. Do 6 pages of calculus to get 0. Like, when I could have used symmetry, you know. So that's why he's burning all of his homework. Okay. Don't burn your labs. Okay. I don't want anybody to get in trouble. Okay, so light scattering cannot cause an n equals 1 to 2 transition. Okay. So what about scattering? So if we have an AG going to an AG, then everything's AG. So, this is pretty simple. It's just AG, AG, AG. It all collapses down to 1 AG, top row symmetry, not equal to 0. So what situations cause this? Well, the scattering rules of 0, staying put, would be Rayleigh scattering. So the light comes in and scatters off and there's no change in quantum state. That's allowed. And so that's the plus or minus 0. That's the Rayleigh scattering. And then plus or minus 2 would be allowed. You can show here the going from 1 to 3. That's a change in 2. And so that would be Raman scattering. We don't have enough quantum states shown on our little diagram here to do 4, but trust me, 4 is allowed as well. It could also do AU to AU. I don't have that one shown, but let me just show it real quick. So what if we started here, in this level? Could we go, let's say, intensity proportional to, let's do AU, AG, AU. Okay. And sometimes we'll just do vertical lines instead of those times symbols. So we can do it this way too. So this is all AU levels. Can we do AU to AU? And let's just do that one. So AG times AU is AU. Bring the other AU down and continue writing your Dirac notation. We can put the square on there if you want. And so then the AU times AU is AG. And so since that is top row, it's not equal to 0, therefore allowed. So what situations would AU to AU be? Well, that would be delta N equals 0, right? Because if I'm in AU, I could scatter with Rayleigh light and end up back where I was. So AU to AU is allowed. And then look at this difference. So this difference here is also plus or minus 2. It could go down as well. So it could go up or it could go down with the Raman scattering. So I still get the same selection rules, whether I start in an AU level or whether I start in an AG level. So that's great. And that, I don't have you do that one by hand. So I did cut you some slack. That's in chapter 6, I think, of my book. I think. Anyway, that's the Raman selection rules, and it's even longer. So in the absorption selection rules, yeah, she's like a version. So the X with just a single X, you have to do integration by parts one time, I think. Don't you have to do it one time? In Raman, it's nested. So you have to do it once, and then you have an X. If you get rid of X squared, you have an X now, and you got to do it again. So it gets nested. And you break in, actually, I think maybe even 3 times. You do it once, and then you get 2 equations, and each one of those needs integration by parts. So it's nested, and you end up with zeros on the odd ones and non-zeros on the even ones. So anyway, so I'd cut you some slack on that. Okay, so let's practice using the direct product table for a point group other than CI. So here's ammonia. And here we have the HOMO to LUMO transition, which I talked about in organic. Am I correct? You did organic? HOMO? Yeah. So it's typically the longest wavelength transition in a molecule. And if it's a colored substance, it falls in the visible range. Many of them, the molecules are so small and the gap is so big, it's only in the UV. But once you get a bigger molecule, it's just like the particle in a box. You make the system bigger, the energy levels crash down and get closer together. It'll move into the visible range. And so we see colored molecules with the HOMO to LUMO transition. So in this case, we have the highest occupied molecular orbital is A1, the lowest unoccupied molecular orbital is A1. And what kind of light can cause this transition? Well, this is interesting because we have now a split. We have 3-dimensional system here. So we don't just have X, we have Y and we have Z. So X and Y both have the same symmetry. So it doesn't matter if I come in with X symmetry or Y symmetry, that's going to be E. So that's one set of problems. And then Z polarized light is A1. So to answer this question, we have one possible transition, but we have 2 flavors of light. We have X or Y light, and then we have Z light. So we have to do this problem twice. So let's go through it. So Z polarized light is A1, X or Y polarized light is E, and so we can set up our transition dipole moment integrals. So this is for Z polarized light. You see the highest occupied molecular orbital is A1, the lowest unoccupied molecular orbital is A1. So we have A1s on both ends, and then light is different in the middle. So we have Z polarized light here as A1, and X or Y polarized light as E. So here's the direct product table for a C3V molecule or other point groups like ethane, D3D or D3H, whether it's eclipsed or staggered. And so let's do the Z polarized light. So we have, this was our setup from the previous screen. And so we have A1 times A1 gives A1. We bring this A1 down. And then A1 times A1 is A1. So it's all A1s. You're going to end up with A1 in the end. And so this is allowed by symmetry. Yay. So Z polarized light can come in and cause that electron to jump from the highest occupied to the lowest unoccupied molecular orbital. What about Z, X or Y polarized light? Now I've done this one kind of in a shorthand. I've just shrunk those to E, and then I did my little bracket diagonally, and A1 times E is what? Let's come up here. Yeah, A1 times E is E right there. So then I have my integral of E, and that equals 0. So this is forbidden by symmetry. So this is just saying that this transition is allowed for Z polarized light only. So we call this one, I'm going to go ahead and write here, put an arrow and say forbidden. Okay. Questions on this one? Let yourself get it. It really is that easy. The trick is getting the molecule right and getting the point group right, and yeah. But the rest is pretty easy. You go up to the character table right here, and you find where the light is. Right here's X and Y. Here's Z. If we wanted to do Raman, I don't have that in the notes, but you have these guys, these interactions for Raman, and you have these interactions for Raman. So we had the same kind of math, A1s and E's, but different experiments with Raman. Okay, let's do rotational energy levels. So this is the rotational energy equation. J is the quantum number in this case. I know it's chilly, isn't it? Okay, so the J, quantum number J. B is the rotational constant. That has the moment of inertia, which is like the mass of the molecule that's rotating around the axis, etc. And notice over here these particular motions. So the rotational motion alternates. So let's say so it starts out with even top row. And every even one of these rotations is top row. Okay, and then the odd ones are the symmetry of the motion. So in water, if we have rotation around Y, okay, let's see, yeah, X, Y, Z. So that's this rotation in water where it's rotating like that. That has the symmetry of B1. So we go to the character table, we have three R's. We have RX, RY, and RZ. So depending on which way it's rotating, you pick that row in the character table. So here's the character table and here's the direct product table. You can see RY right here. And then we have, so can this rotational mode be excited by direct absorption of light? Well, now we're in an asymmetric system. The ammonia was a C3V molecule. So in a symmetric top like ammonia, the X and Y are on the same row. They have E symmetry. It's doubly degenerate. But on an asymmetric molecule that doesn't have threefold symmetry, like water, X, Y, and Z are completely broken apart. They have totally different symmetries. So we have three problems to do. We have the ground state A1 and the excited state B1. That's the same for all three, but we have X polarized light, Y polarized light, and Z polarized light. So we have all three of these rotations, and we have the different light that we have. So for Z polarized light, this is what we end up with. So Z is A1, so we have A1 times A1 gives A1. And then B1 times A1 gives B1. That's not the top row, okay? So we would say that one is equal to 0. Then we have X polarized light, which is B1. So B1 times A1. And you start to get an idea of, look at this, anything times A1 is itself. So like here's B1. Anything times A1 is going to just be returned because A1 is just all positive ones. You know, all its characters are +1. So if you multiply anything times +1, you're going to get that thing back. So here, you notice A2 is times A1 is A2 and so on. So that helps you know what you're doing and to check your work. So B1 times B1, B1 times A1 is B1, and then B1 times B1 is A1. Notice the diagonal. See the diagonal is all A1s? So anything times itself. So if I have A2 times A2, I get A1. And if I have B1 times B1, I get A1. So that's a helpful thing. So you might be able, just in a few days after doing these problems, to do this one totally by yourself without the character table or the direct product table, right? Because you've got something times A1. That something comes down. Okay, and then you have something times itself, A1. Yeah, so that's nice. There's a symmetry to it. Ah! Okay, so this is non-zero. And then let's do y. Oh, I didn't do y. Let's do y. Okay. ry times y times a1. So ry is b1. We go find y in the character table, so y is b2. And then the ground state is a1. So let's pair them up. b2 times a1. Don't even look at the direct product table. Tell me what that's going to be. b2, because it's something times a1. So b2. Now this one is, even I want to check my work on this. This is a b1 times a b2, and I'm thinking, I don't know, right? And so we got to go over here, and we see b1 times b2 gives us a2. But yeah, I would want to use the direct product table for that one, a2. Now, don't be fooled by that tricky letter A. This is not top row. A1 is top row. This is not top row, so this is equal to 0. So there's only one allowed polarized light that will cause this transition to occur. Okay, and that would be a Y polarized light. Okay. Any questions on that? Vibration levels. We could do the same thing with vibration, and vibration alternates top row and so on. So this is top row. Can I just put TR on that? TR. So TR. TR. Okay, and then the odd ones are the symmetry of the motion. So if we're looking at the asymmetric stretch for water, that's this one where the hydrogens and the oxygens are stretching asymmetrically, then that's a transition in the y direction, and y is B2. So we would ask what kind of light is allows this transition. So it's very similar to what we did with rotation. Set all these up, and we end up with, for Z polarized light, we end up with B2, which is equal to 0. For Y polarized light, we end up with A1, which is not equal to 0. So this one is allowed. And then for a Y motion, will be B2 with X polarized light. So X is B1, A1, B2. So we're going to see this, that's B1. And then this is going to be A2 because we just did that. And that's equal to 0. So that's forbidden. So the only allowed one is Y polarized light, allowing the Y direction of the vibration. And in vibration, that's something that you can take to the bank. If it's a Y vibration, Y polarized light lets it. If it's a Z vibration, a symmetric stretch, then Z polarized light will allow that one. If it's some sort of other molecule that has X vibration in the X direction, then the X polarized light would allow that one. And that's in infrared or vibrational motion. Okay. That's all I've got. So we're getting a little gift today. If there were any questions from the test or anything, y'all can come up. The tests are upstairs, and I've got class next, so it's not a good time to look at that, but fast lecture.